Good. So were there any, or are there any remaining questions regarding our formulated model right now? Anything you want to clarify before we go into estimation? Need to see you, so that's better. Yeah. No, it doesn't seem to be the case. Good. And so this phase validity, in a way, this is also always where, from my perspective, computational neuroscience then stops. So they are happy with then reproducing kind of things that look like real data, but we have to do a little bit more because we want to do statistical inference. And so the remaining part then for today would first talk about model estimation and also validation, by which I mean to look at how well we can actually recover both our parameters and models, and then in the very end to apply the formulated model to the data in this perceptual choice task that I showed you in the very beginning. The model estimation approach that we use is maybe a little bit more, I don't know, is it standard, but it's definitely more standard than this whole thing about talking about task agent and behavioral models the way I did. So the model estimation uses a maximum likelihood approach, a numerical maximum likelihood approach, and for model comparison, then we use a Bayesian model comparison criterion, and we use a random effects procedure. So in a way, this is, if you read these introductions to computational behavioral modeling, this is also what you would find in those introductions. Although the most challenging, so in a way, it's kind of a recipe and a pipeline you can follow. The most challenging thing, although, is to first establish the thing that you want to maximize, namely the log likelihood function. And this is where still a lot of thinking has to win. So let's start. So what we do is we do, like I earlier explained, we do estimation of the parameters at the participant level, and then we do our group level analysis based on participant data data evaluations. As I said, this is not the only way you can do it. Hierarchical modeling is possible. And as I also said, this is coming from cognitive neuroscience mainly. Good. So what we then always need to do first is to actually formulate and implement the log likelihood function, so the probability of our observed data under a given model. And I formulated this here in a general case where we have a parameter space for our model M. And from the models that I've shown you that we look at, the zero model, the control model, doesn't have a model space, or the model space is fixed at 0.5. So in this case, we just evaluate one log likelihood. The other ones, the 1D models, there we have the parameter space, for example, for the action noise being just the interval from 0 to 0.5. So these are these parameter spaces. Of course, we get a number that is our log likelihood, and what we need, or what we look at, of course, in the log likelihood function is the probability. In the likelihood function, the probability of our observations under a given model at a certain parameter setting and under our experimental constraints. So our experimental constraints in this experiment are these contrast differences. So we know the contrast differences, and conditional on the contrast differences, we then look at the probability of a certain action. And as I've shown you before, we have derived this implicit distribution of the probability of one action given a contrast difference based on the definitions of our agent and behavioral models. Then we assume independence so that we can actually sum over the logs of these probabilities. And this is one of the parts where also when writing this up, I will have to do a little bit more work, because some of these things in terms of the actions that we have already conditional independence given the contrast difference by definition of our experiment. And in other settings, this might not be the case, and independence is assumed. And this is quite easily to confuse in terms of the log likelihood function. So it's quite easy to implement that and sum up all the log probabilities. But sometimes, at least for me, there's a certain feeling of, is it really okay that I just sum everything up here? And then it helps to establish these independence probabilities analytically. What you find here is, I didn't say that in the very beginning, when I use parameters and things here as a superscript, I always mean that these are not random entities, and if a condition, then it's condition, they are always random entities. So these are not random in the current setting, because we assume that as experimenters, we have access to the contrast differences, so we know them. So that's kind of the log likelihood. It's not fully explicitly all explained in this presentation. And there's also a little bit of ambiguity and uncertainty in my thinking still when it comes to this log likelihood function, especially like what I just explained. So there you can wait a little bit for the tutorial, then there might even be more clarity. Good. But nevertheless, of course, the log likelihood function is a function of the parameter vector. And also, even if there's some analytical unclarity, as we do these validation studies, we are very confident that what we're doing makes sense. But analytically, there might be a little bit of stuff to gain. So this is our parameter vector. These are just the number of blocks and trials per block. So we just sum over all valid actions. So we take all valid actions that we've recorded and use them to inform our parameters. For cognitive neuroscience people, reaction times are not looked at here. I mean, that was clear all the time, but here it's specifically clear. Although in Sarah's experiment, we will also apply the same framework when dealing with reaction times, and she can tell you more about that. This I explained. This I also explained. So this is the log likelihood function. This is if you're programming this up, and also you look at the code that you find there, the log likelihood function is always fairly similar to the simulation function. So if you simulate the agent, you of course sample these probability distributions. And if you evaluate some data in light of an agent, you basically only look up the probability without then sampling the agent. So I definitely, for those people who are now starting this, if you are at the point where you can simulate your agent, you are quite close to also having the log likelihood, at least at the implementation level, fine. With certain restrictions. So for example, if you have internal random things, for example, like we have here, then you of course will not, so then you will actually need to, there will be slight deviations between your simulation of the agent, where you simulate, for example, in this case, an observation, and here then you read out the probability of a decision averaged over all agent observations. So there are slight differences, but if you are, especially if you have internal random variables, so internal noise in the agent, but in general, if you can generate data with your agent, you're fairly close to the log likelihood function already. And once you have the log likelihood function, then from the way we deal with it, you are basically almost done with the full model estimation procedure or the implementation of this procedure, because We then usually use numerical minimization methods. So in this case, the SciPy optimize and SciPy minimize to minimize the negative log likelihood function, which works reasonable well, depending on the log likelihood function. So for this case study, Nelder-Mead, so this derivative-free minimization works quite well. We will see one example where it doesn't quite work, where we actually need some constraints and where then some bounded optimization is better. For what we'll then show you on Friday, where we have this Koller-Wagner model, because these very simple Koller-Wagner with a learning rate have really horrible log likelihood functions there, and especially then if we have these two, if we have another parameter, they actually use brute force, so just measuring the log likelihood over a discrete version of parameter space and then going to the maximum and identifying that. So the costly thing, or what takes time in all of this, is of course always to evaluate for each parameter setting the log likelihood function, which involves the entire code of the agent, the task, the agent, and the not the task, because you condition on the task, but the agent and the behavioral model. So it can take a little bit of implementational time. But maybe I will soon be in charge of some cluster, and then everything will be parallel and very quick. Yeah, but that's a different topic. Good. So this is how we estimate the parameters. So essentially numerical maximum likelihood estimation after establishing the log likelihood function. Then for model comparison, fairly standard, we use Bayesian information criterion in its original form, not in the form that you find everywhere and then get confused because it's negative and the lower values are better, and or the other way around or whatever. So I just use the definition in the Schwarz thing, which uses the log likelihood function. So if the log likelihood gets higher, the Bayesian model comparison criterion gets better, and what is punished are the number of parameters. So Km is the number of parameters for model n, and it's multiplied by the number of data points. So Km is the number of model free parameters, and n is the number of valid actions. So for those people who are new to this whole thing, I assume that most of you, all of you, know the differences between maximum likelihood estimation and Bayesian estimation. It's kind of a mixed approach that we use here. There's not so much to gain by doing full Bayesian estimation. And then this big way of doing things is some way to do model comparison and doing it formally correct in some way, in some sense, by accounting for the number of parameters, even if you just do maximum likelihood estimation. So essentially, and this is the intuition here, if you have higher maximum log likelihood, you have better model fit, so you favor accuracy, but you punish more model parameters, so you punish the complexity of the model because you don't want to fit noise. So that's the very basic intuition for that, and we follow that. And of course, there are many variants for all of this and things to discuss and so on, but this is what we do here at the participant level. And then at the group level, we actually, in general, use this random effects model comparison approach that we get from the SPM world of things. Here, actually, I haven't kind of integrated this fully, because then I would have to write up certain things about that. So I use a simpler approach. So in terms of the group parameter estimate, I just estimate the parameters over participants, and as the group Bayesian information criterion, I also just compute the average. This is just, you can call this a fixed effects model comparison if you want. I'm just doing it currently to actually look at model comparison. I want to put in the RFX, but I'm just not there yet. So I'm just using a simpler version, and the difference to the RFX will also not be much from what I see across the different participants, because they are all very similar. So very simple. In each participant, find the maximum likelihood estimate and get a group estimate by averaging over the single participants, and the same for the bigs. And in general, for this, we use this Polya-EARN model as implemented by Rigoux, but I want to look a little bit in detail into that, and I haven't done that. Anyway, and as I said all the time, one could also do this whole thing hierarchical in the sense that you only that you have a real mixed effects model, and we might at one point implement this. It's just this is actually more a question of implementation in terms of the results that you get from doing this two-level random effects approach or a hierarchical random mixed model approach. This will hardly differ. Good. As I said earlier, to do that, and this is where the problem comes in with defining the log likelihood function, usually from this way of developing the model and having it being a nice generative model to produce experimental data, you might not have all the distributions that you actually need. For example, as I said earlier, what we need is the distribution of the distribution of the agent decisions given the contrasts. And what we had discussed was the belief state, and that we found an analytical analytical formula for that. And what we also, I've already shown you that briefly, and now I'm telling you why we actually need it. In the log likelihood function, we need the probability of the observed action given the contrast difference, which we provided to the participant, and we need this probability for each trial to take the log and then use it as our in the log likelihood function. This we only get, or we basically get from embedding the probability of the decision giving a contrast difference by applying our Bernoulli distribution. And this I haven't fully celebrated earlier, because this is what, like I said, this is what Rasmus derived. And this does this averaging over internal agent observations, in an analytical manner. So if you read this Marr paper that I highlighted earlier, he emphasizes this quite a lot, and it's of course also important that our model assumes that at each trial the the agent generates a certain observation. But we don't observe this internal agent observation. We only observe the action, which is, of course, is already only an indirect reflection of the decision, which is following from this internal agent observation. And the easiest thing that you can do to account for the fact that you don't observe this internal observation is to average over all possible ones. And this is what Rasmus did here, and which yields this form, which earlier, let's go back briefly to that, which we had validated here. So this accounts for the averaging over the internal agent observation. I think I said something about the uniform here, and that didn't make sense. So this accounts for the averaging over internal observations. Rasmus, do you want to add something to that?
No.
Nice, good. There is no button, I think one can press. But this is fairly important if you have these internal agent variables that you don't observe. This is also where you can, if you want, say that brain imaging is interesting, because you might be able to read out internal variables of these agents using brain imaging. But whether that actually helps, this is what Rasmus' postdoc project, I guess, now is also about. Sometimes this is not that much of a problem because we actually don't assume any internal agent noise. So for example, in Lilith's projects, we usually had very clear stimuli so that there were still hidden states, but they were kind of rules of the environment. But we assumed that there is no internal noise that that confuses the agents in its inference about what's going on. So that's specific to what's going on here. Good, let's go back to this. Yeah. So these are necessary, otherwise you can't do your log likelihood estimation. Yeah, so one has to derive them or at least approximate them. And they can be, of course, specific to what you're currently doing. But then once you have done that, one can look at the validation. And this is, I think, also quite important. So, of course, we want to, in the end, make some conclusion about experimental data, but to actually validate your implementation of your estimation code and also to understand the model better. I actually don't know what is more important. So one thing from these validation studies is that you understand your model better. The other thing is that you make sure that your code works. So what do I mean by validation? I mean to simulate data based on the task, agent, and behavioral model, or based on the presented task states and, in this case, contrast differences, and then simulating the agent and the behavioral model to simulate data, and then apply the estimation approach that you want to do, namely maximum likelihood estimation and model comparison to that simulated data. So if you read the cognitive neuroscience literature, some people say essentially what you should do is fit your model to participant data, and then you find some parameters, and then make sure that you can recover these parameters. That makes sense, and it shows that then that so that your parameters of interest are recoverable. So we do a little bit more in the sense, but we also have it quite easy here because we have very few parameters. So we try to basically generate data over the entire parameter space, and we then try to recover the most parameters. This works, and this is why we can do it. This works if you have small parameter spaces. If your parameter spaces get larger, this gets more and more computationally expensive because you get combinatorial explosion. And then actually this approach that you find in the literature that you should recover your estimated parameters also makes sense. But also it will get a lot harder to recover them, I would suggest. Okay, so what do we have here? So this is now data generated with our P1 model that has this free perceptual uncertainty parameter, and it's generated with a perceptual uncertainty parameter of -6, so fairly certain, to -1, so fairly uncertain. And the question is, if we look at the log likelihood function, the average log likelihood function over many participants, where does this log likelihood function have a maximum, or first of all, how does the maximum likelihood, how does the log likelihood function look? And it doesn't look that nice here. It looks a little bit, what's the word? Doesn't look very smooth here because I only used 5 parameter values. And that's why it looks a little bit kinky. But the essence we can see. So if we generate with 10 to the power of -6, then the maximum of the log likelihood of the likelihood function, of the log likelihood function is actually at 10 -6, and this is what we want to get. And the same then for -5, the maximum is at 10 -5, and so on. Of course, I might be doing that. If I go to a little bit higher resolution in terms of parameter space, then we would likely also have this thing look a bit smoother. What's always a little bit annoying about log likelihood functions is that they sometimes, depending on how you look at them and in which resolution, they have these sharp drops somewhere, and then it's a little bit hard to find how you should look at them to actually see the interesting features. So log likelihood functions can be a little bit annoying, but so this, for example, would be actually quite a nice log likelihood function. This is for the tau parameter in our P2, which only has this action noise parameter. And this, at least here, looks almost smooth, although I only have like 5 values also, or 6 values also in this parameter space, so 0, 1, 2, 3, 4, 5. And you can again see that the maxima are where they're supposed to be. Yeah, this is an example log likelihood function for the 2-parameter model, where the 2 parameters were yet 10 minus 4, so this, and tau 0.3. But here you also see for this 2-parameter model that you kind of get this kind of crest-like behavior here, where you have very similar log likelihood models for parameter combinations. So this is then usually a sign that it might not be that easy to recover the parameters. Of course, an easier way to look at the question of parameter recovery is to look directly at it. So you simulate, in this case, so I simulate here model P1, analyze it with model P1, and if my parameter is 10 minus 6, what do I get on average? And here I get 10 minus 6. So the gray line just shows what I should get. The blue dots show what I actually get. Again, this is always the log likelihood functions for data that has the same properties as our experimental data. So it's the same number of data points, and it has the same hierarchy, so participants and number of trials. The difference here is still that here the contrast and the states were sampled again, and maybe then sampled a little bit different than in the experiment. However, I already did this also with the conditional on the experimental contrast and states for this, and this looks exactly the same. These are one thing that one always needs to keep in mind, that when doing the experiment, one samples these distributions, and it might be a little bit different from pure simulation, how these recovery things look like. One thing that you don't see here is a blue dot here, because this blue dot here is somewhere up here. So there seems to be, it seems to be in a certain, maybe it's actually this bad participant or something, where if I use, this is based on unbounded Nelder-Mead minimization, where the parameter recovery goes horribly wrong, and then even in the average is still completely off. So this is why you don't see this dot here. So one thing one can of course do is to bound this and basically just reject any parameters that are somewhere where it's completely unreasonable, and constrained to that. But yeah, of course, one also doesn't want to just allow so it makes sense sometimes to constrain a parameter space. So for example, here it's naturally constrained between 0 and 0.5. If we would also have a 0.5 to 1 in there, then things would switch around, and it would not be identifiable because it's the same thing, but the other way around, and everything would be very weird. So here it's completely clear that we need to bound this. Here it's a little bit less clear that we need to bound it, but numerically it's at one point clear that we also need to bound it. In any case, parameter recovery works fine, except for this one participant, or that isn't this participant? I don't know. It doesn't work once, and it gets a very large value. So here maybe I also want to use a bounded parameter recovery after all. If we go to a multiple-dimensional parameter space, it's of course a little bit less clear of what kind of bias we want to look at. And here what I use is kind of the deviation between the two-dimensional true parameter and the estimated parameter, and then the norm of that. And you can, in a way, also see here, if you are somewhere where the noise is relatively low, then you get relatively good parameter recovery. If you go to high noise scenarios, actually the parameter recovery gets bad in this case. This is quite interesting here, because here you have a high noise scenario, but the parameter recovery works quite well. Yeah? So it's high noise, but because the noise is completely due to this one parameter, it's quite clear where this is coming from, and the parameter recovery can sensibly allocate this variability to this parameter. Good. So that's one thing, to make sure that the parameters can be recovered. And then the thing that takes the most time in terms of running these analysis is model recovery, because there you analyze each model and data generated from each model with all other models. And so you fit to each model, so you fit all other models, and then if you simulate each model with multiple parameter settings, then for each model you have, for example, 10 parameters, and then you analyze this with 4 other models, so it gets quite large. And then the question is what happens, and how this depends on parameters, if one has the opportunity to look at it. So again, model recovery, here we're looking at the BIC values, and the winning model is just the one with the highest BIC. So here this is data generated from model P0, and the highest BIC is taken on by model P0 and lower BICs by the other ones. So P0 is the winning model, so we can identify the P0 model, which is something. Then we have data generated from model P1, and the highest BIC is then attained by model P1 until a certain point where actually the null model gets better in the scenario, and this makes, of course, some sense, in the scenario where this perception uncertainty parameter gets fairly low, and the output of the model becomes fairly random, then the null model actually wins. And of course, the null model is not punished in terms of parameters, because it does have only 0 parameters. So if you have a 0, if you have full noise, and full noise generated by a model with, or analyzed with a model with 1 parameter, so, compared to a model with 0 parameters, it makes sense, of course, that the model that doesn't have a parameter, because it's not punished, then wins. For P2, what do we see? We see that, for P2, we actually see that P2 wins. Is that P2? I guess. But P2 can also be emulated quite easily by P3. So actually here, P3 seems to be a little bit better in accounting for, is that P2 or P3? Who thinks that? So I think this is P2. I would actually need to check with the in the data, because I think P3, that's a little bit lighter. No, it's P2. Sorry. I think we have it in the. I looked at the other model. So on Friday we will see where this is actually happening. But this is still P2. So here P2. It's P2, right? So this is P3 here, that's lighter than this. So P3 is definitely lower in terms of its BIC. P2 is higher in terms of its BIC, so this is P2. Colors. So again, kind of works okay. This P3, there things go a little bit more wild, and this is only from 10 participants, and it's going along the diagonal of P3 parameter space. so I haven't really thought much about this. The thing is, if you maybe we don't discuss this right now. One thing, because I don't have a story to tell about this. One thing is that you always need to be aware of that certain models can emulate the behavior of other models. So for example, if you have a model that has 2 parameters and you have a nested model that has one of the parameters the same as that, then of course the model with more parameters can recreate the behavior of the nested model. Usually the model with the higher number of parameters then gets punished because it has this additional parameter and it doesn't win the model comparison. So for these 3 models here, I think I'm quite happy with the model recovery. And if I read the colors correctly, then I'm actually happy. P3, I have to think a little bit more about, and also I want to finish that with the entire data so that I get a little more sense of that. But in a way, it makes sense that if you, for example, here, if you go to the, very low perceptual certainty and very high noise, then of course P0 takes over again. Good. So this is kind of the validation studies or the validation things that we do. What they help is, in understanding the models, how they behave as parameters, and they also provide you with confidence that your code is actually working. So often, one feels, especially if coming from an experimental setting, of course, you feel like you would apply, you have now your model, you have developed it, now you want to apply it to the data. But then you feel much better in applying it to the experimental data if you have validated in vitro, because you don't feel like maybe you have a horrible bug in there and all your experimental conclusions are wrong. Because you have validated that and you know that it behaves in simulations as it should behave. Good. And then I will now show you what actually comes out if we apply to the experimental data. But are there any questions regarding this model estimation and comparison procedure? Anything that you would like to clarify in terms of the simulation or something? No, not right now. The good thing is, that's also what I do. If you turn off your mic and your camera, sometimes I eat then and so on. So sometimes if you're then prompted to respond, you might not be willing to respond. Good. Finally, model application. So now actually applying these 4 models to the data. Of course, you can now view this in 2 settings. Either you can see this as a tutorial application and it's fine, or you can actually see it as an interesting result. I think on Friday the results will be a little bit more interesting because we can really trash Riscola Wagner learning rate models on Friday. Today it's less spectacular. It's a little, it's in a way a little bit what one expects. So this now shows the application of these 4 models to the actual experimental data, so not simulated experimental data. And we see here the BIC, so and this is red normally, so low values is not good and high values is better. They are negative, but low and negative also means low. So the P0 model has the lowest BIC, the highest BIC is achieved by the P1 model, which is actually the model without any action noise. Then the action noise model is a little bit less good, and the P3 model, which has 2 three parameters, doesn't win. So I think this in some way replicates what we also did with Erasmus previously, because in the current setting, I think we decided, or at one point we decided we don't want an action noise parameter in Erasmus experiment. And in a way, this analysis here shows that we also don't need it. I don't know whether we actually in Erasmus project already showed that we don't need it, or we just decided we don't want it. In any case, this shows that we actually don't necessarily need it, which of course has to do with the fact that our, on average, our psychrometric function here is almost up to 1 and 0. So we don't have this strong offset that is then best explained by actually this pure action noise parameter, whereas this little bit of this little offset here to 1 in the experimental data is not enough to incorporate one more parameter here. So this is why P3 doesn't win. So the model evaluation, the winning model, which this is of course mimicking protected exceedance probabilities here, because I assume this is what they will come out, tells us that our P1 model wins. Here, I thought maybe it's just on top. I think it's just missing. What I actually wanted to plot here on top of what the data that we've seen previously is also the predicted group mean, which is either it's actually, I think it's just missing. Maybe I just forgot to plot it. Here, so there should be another line which is very close to this group mean line, but in dashed form, because that's what the model predicts. No, I know why it's not there, because I was going back and forth in how to generate this prediction by the model. Of course, you can create a prediction by the model by now simulating it and then doing the descriptive analysis or descriptive statistics analysis and then plotting that on that. Or you can come up with the theoretical prediction of the model. And I actually wanted at one point to come up with a theoretical prediction of the model, which is of course the probability of an action given the contrast. And this is the probability of the action given a contrast under the group maximum likelihood parameter estimate. So this is the theoretical prediction of the model. What one can see is that for that there, of course, this is at 50% at zero contrast difference. This seems to be a little bit of a rightward bias. So one could, of course, also create additive biases and an additive bias in this model. We actually tried that in Erasmus experiment, and there we also, the model comparison, I remember, came out that the additive bias did not really win model comparisons, because this very little deviation here from 50% again was not worth enough to have another model parameter in there. But still, from looking at this, when I saw it, it feels like because it's really on one side most of the time from the group data. If one looks at the if one looks at the BIC from the single participants, that's not that interesting. Mainly the P1 always wins, except for our still for the P31 it also wins. But you see that also makes sense with this very bad subject that the interesting models are not really much better than the null model. This is how the single participants fit look, and there you can see that actually the biases go both ways. So sometimes it's the real data, which is here, this light blue, is a little bit to the right of the predicted model fit, and sometimes it's on the left. And here again you have participant 31, where we essentially predict a straight line, And participant 22 is also quite bad. This is also quite bad. Also quite bad, but some of them are also quite good. For example, P2. Good. So the summary then of the whole thing that of this application scenario is the following in a typical perceptual choice task. Psychrometric functions, like they have been looked at and forever in cognitive neuroscience, can be generated by this internal perceptual noise agent models. There are papers that have done something very close to this before. So I know that there is a Manish Sahani paper that is very similar to that, but it's quite surprising how few papers are there like that. So usually what people do is if they use these perceptual tasks, they fit directly a sigmoidal function to this. And then you can say, yeah, of course, this you can think that this is generated from internal noise models and so on, and you carry this theory with you. This just does it a little bit more directly. Like I said, it's more of tutorial nature, and Rasmus' real experiment is about combining this with the learning stuff. But still, I think it's there is not that much stuff, that many papers that actually do this in this way in the literature. Perception noise and action noise models can be distinguished. That's from the model validation, and from the model evaluation, we find that we actually don't need to include an action noise parameter. So the perceptual noise here suffices to explain the experimental data variability. Of course, this is also in a way already how this whole thing was titrated in the very beginning. So of course, if one would not have made sure when we set up this experiment that people get roughly to 1 and 0, then of course that would be a little bit harder. So the results maybe from this application are not that groundbreaking as they are from the other stuff that I will show you on Friday. But these are the results that you can then have based on such a study. Good. And that would be the first case study. So questions, comments, anything? I think at least Rasmus will have questions or must have questions.
Not necessarily.
Did you sleep through the whole thing?
No. I watched it, but I don't know. I think I don't have questions.
Okay, so do you remember? So I remember that we definitely say. So I remember that I said let's not put on noise onto the decision of the agent. But did we ever actually do that?
Yeah. So in the very beginning, when we still used models that were a little bit more similar to these, what you just named, psychometric function models with sigmoids, we also had a lapse rate.
Yeah,
if you remember.
Yeah, I remember. So yeah, I remember. So there, of course, you fitted a psychometric function with a lapse rate, and this is of course the equivalent to to this. But then directly we never did that, right?
No. So when we switched to this framework that you just discussed, we still trusted our initial ideas that a lapse rate is, or like our validation that a lapse rate doesn't really, it's not really necessary.
Yeah. And this basically then proves scientifically that we actually don't need. I mean, what it means is, people really, so it's only the internal noise, and then people, I mean, what it means is if people, so the psychological interpretation is that if people decide that it's on the left, they also report that it's on the left. Yeah. But I think also but I think also the whole power of distinguishing decisions and actions is, I think it gets clearer if one actually allows for stochastic decision policies. Then it gets really clear why this is so important. Here it's a little bit maybe redundant. I don't know. Lila, do you have something to say about this decision versus action stuff?
I was thinking about it. I really like this proposal, and because like one way I was getting my head around it is that the what you call decision now is what I called to myself like an action, and then what you call action, I call it as an observable action.
Yep.
So this is,
and like
and
I said, so sorry for interrupting, but like I said, this calling this decision an action is completely arbitrary. I don't think it's more valid in a way to call it action or observable action, or to call it decision and action. I just I found it useful here to call it decision and action because here it's always perceptual decision making, economic decision making, and then we have this Markov decision process things with actions, and we were never so. And so here it works nicely in this kind of nomenclature. But you wanted to say something else? Sorry.
Oh yeah, no, I just wanted to add that I really think that this becomes very useful once one starts to think about, or at least for me, when I start to think about exploration, because in the literature, many times the softmax decision rule that you mentioned, that we also in our project use as our data analysis model, that's interpreted as stochastic policy of the agent, as like a stochastic or like a random exploration, so that there is no distinction between what is part of the agent and what is part of the agent's policy and what is part of just our observation model, or what is our observation model. So no, I definitely agree with this. What you added, that, for instance, there, like once you start considering random policies, that becomes very interesting and important distinction.
Yeah, but also then harder to estimate. Yeah. Good. Any other questions or suggestions or stuff? Doesn't seem to be the case.
I maybe just wanted to add that I think it's a really nice approach to write a tutorial from this, because I mean, as far as I know, there aren't many tutorials on agent-based behavioral modeling, and I think that there is definitely a need for that. So, or I would really like to see like having basically like a recipe book for that. So I really like the format. And thank you so much for initiating it again.
It's fine. You don't have to. It's fine. No, I think the nice thing is, or for Rasmus and for you, it's a little bit annoying that this wasn't there when you started your PhD, essentially. So you would have so much easier if that was there. But of course, it's also just the result from working on these PhD projects with you guys. Yeah. Good. Then, if there are no further questions, then I hope this was not too boring, although we didn't get Zoom bombed, which is, of course, always a lot of fun.